Good morning, ladies and gentlemen of Caucus. Welcome to room 15. Where?
Learning never ends.
Learning never ends. Got a t-shirt or t-shirt order. So we'll see who's good. I had you down on the right, on the left side.
Y'all heard, right?
Well, I want the chicken one.
Or
Oh,
y'all
the chicken
got
one?
it?
Yeah, I want the calculus one.
So you change that one?
Okay.
Still medium.
Yeah, okay.
Okay. I was thinking. You wanna go out to my car?
Okay, good. So we got 6 of the 2 kinds of people, and we got 11 of the chicken one. That'll be good. I mean, they're both good. They both have a humor.
A little humorous.
A little humorous. I have a friend of mine. Her name is Karen, and she's a calculus teacher out in California. And she taught me computer science a few years ago, and I sent her a couple of those shirts. She said she really liked them. She also liked the calculus on. Yes. All right. I appreciate the artwork here. That's very, very clever. Good job.
Ad did that.
Thank you. Ad did that. Now, I do have a feature today. I want to start out with. I have a joke of the day.
Oh.
And I don't know. I'm going to try to do it if I can. So it's not going to be an everyday thing. But the person who suggested it was Iceland. So it's Iceland's suggestion. So I have one I thought would be pretty good. See what you think of it. Do you know why pediatricians get angry all the time?
Why?
Because they have little patience.
I would say that's very good.
You like that?
I'd laugh.
Very good, very good. Anyway, so that's a joke for you. I forget where I
That's a good one.
Yeah, I'm good.
I think my wife might have given
You
it.
should have said that on camera.
It was on camera.
Oh, you already started it?
Yeah.
We said Learning never ends?
Yeah. It's just part of the thing. We recognize your artwork. We've been talking about t-shirt orders, and so and we left it right here yesterday. And so I'm going to have to go. I'm going to go ahead and desecrate the good artwork here. So I hope Addie's going to forgive me for what I'm about to do. Addie, forgive me for what I'm about to do. No, here's
You
one.
duplicate this slide.
Okay, I guess we do that.
All
All right.
There you go.
All right, it's still there, right?
Delete all the slides.
You can see the slide is still there above it, right?
Yes, I can see it.
Okay, good. And I'll have to save it, make sure it stays in perpetuity, right? Okay, very good. So now we have this one right here. Find all values between x-intercepts for which Rolle's theorem holds for the roots. And so I kind of left you working on this as of yesterday. Does anybody get any place on this?
I got somewhere. I forgot where though.
What I'm going to try, it says confirm using a calculator. I'm going to go ahead and try to do this a little bit without a calculator. So if we I want to go ahead and write this in factored form. What's going to be our factored form of this? What's our common factor here?
X squared.
So we got x squared, so we're going to have 3 minus x squared, right? Is that right? Or to make it easier, I'm going to put negative x squared, then I'm going to put x squared minus 3. Can I do that? Okay, so find all values between the x-intercepts for which Rolle's theorem holds for the roots of that. So how do we find the x-intercepts from this? What are the x-intercepts?
It'd be 0 and
X equals 0, very good. Where else? Also x equals?
3.
No.
Nope.
No, it's not 3. It's going to be this.
Plus or minus.
How do we get plus or minus square root of 3? How do we do that?
You said x squared minus 3.
Yeah, so Lexi said it. Okay, Lexi is trying to get ready for advanced calculus. She's going to be taking over at her at UT Tyler, right? Lexi, is that right?
You're right.
You got to commit.
Paul does calculus classes.
Yeah, 3 calculus classes, 1 differential equation. That's what I had too. And so that's where we get our zeros. And so now it says find all values between the x-intercepts for which Rolle's theorem holds. So if we draw this out, coincidentally, it's one of these things that we've been doing in pre-calculus now. We got minus, and we're going to be, it's negative. So this is going to be odd positive, odd negative, even positive, even negative.
Oh, it's gonna be
Even negative.
Even negative.
So we're going to come here, so we're going to start low, end low, right? So we come up here, and we're here to negative square root of 3. Do we go straight through here?
Yes.
Yes. Then we come here, and then we get what happens here at 0.
It goes right back down because of the multiplicity.
Yeah, the multiplicity. We got the multiplicity of 2. And that's one of the things. Yeah, odd, even, right. So we had good cheerleader stuff going on here. We had that actually during pre-calculus today a little bit. Chelsea was helping us with pre-calculus today on this. Haley was helping us too. So anyway, if you did graph this in the calculator, this is what you, anybody graph this in the calculator yet? Because if you did, you saw something look like this.
Yeah, you did.
Right. How confident am I of that?
Very confident.
Very confident, very
You
confident.
experience.
And then it says find between all values between the x-intercepts which Rolle's theorem holds. So how many of those values should we see here between the x-intercepts? We should see here and here, right? So we know, so what's our average rate of change between the x-intercepts?
Then the x-intercepts, the average rate of change.
It'd be 2x.
What's our average rate of change between the x-intercepts? 0.
I'm just kidding.
So average rate of change equals 0, and it has to be that for Rolle's theorems to apply, right?
The interval of negative square root 3 to positive 2.
Yeah, over that interval, but we go ahead and find that. Let's go ahead and work that out. How do we utilize this? We do what next?
You find the
Yeah.
y value. That's but yeah.
So what is that going to be? 6x minus 4x cubed. Is that right? And then we do our factoring out of that guy. So what do we have? What's our common factor?
Mr. G, I have a question. Why did you draw lines
Yeah.
on the maximum?
Reading it all. Because there's, like.
The same
no-
differential.
Yeah, what I did, that's a good question actually. What it is, I'm trying to demonstrate that we have horizontal tangent lines at those maximums.
So anytime you have a maximum or a minimum, you have a horizontal tangent line?
No, only if it, like, flattens out like that.
Yeah, now we saw an exception yesterday where we showed one of these where we didn't have a horizontal tangent line. Remember that?
It's not a smooth curve.
It has to be a smooth curve, which we know we have because this is what kind of function? A polynomial function, which is all smooth curve, right? Or line is polynomial. So anyway, what's our common factor here? 2x, right?
Right.
2x, and this is going to be 3 minus, what do we have left?
You're left with
2
2x
x squared. So if we set, so definitely we have 0, but we set this equal to 0. We already know that, but we're interested in these between the x-intercepts. So we already know that, that's the same. So we got to set this equal to 0. So we have 3 minus 2x squared is equal to 0. And so how do we solve that? Yeah, you can do that. You could add 2x squared. So I'm going to put 3 equals 2x squared, and so x is going to be what? Plus or minus square root of 3 over 2. That's what it should be. Let's see if it is. And so that's going to be the x value So let's look at our calculator here. To me, this is the fun part where you actually get to go and test it out. So you go 3x squared minus x to the fourth power. So 3x squared minus x to the power 4, zoom 6. So that looks exactly like we thought it would, right?
Yep.
And so we're going to go ahead and test it. Second trace 5, our second trace maximum, right? 4. So we have left bound, enter, right bound, enter, enter. So 1.2247, so on, right? 1.2247, 1.2247.
Mr. G, you just found the maximum?
Yeah, 1.2247. Whoops, oops. No,
When you do this, apparently you're just trying to find the middle in between like the x value of the middle of the weird looking.
So you're trying to find where, is it not, it's not in the origin?
See, same thing, right? 1 point, so we know that's good,
Yes,
we
is.
tested it.
Like the x value
So
of the
this is the, and it says values. That's another thing about values. It doesn't say x values. But I think they mean x values for that. But coincidentally, we do have y values too, right? Second trace 5,
So we're not trying
not
to
second
find
trace
what
5,
is
second
the
trace
origin.
4. So we go left, let's see what it is.
What x is these points? It says find all values between.
So it's 2.25 is the maximum, and that occurs where x equals plus or minus square root of 3/2.
For which rolls for your.
So yeah, these would be the values of c. Remember we had the value c, we talked about that. Where's that? So anyway, these would be the x values, and that value here would be 2.25.
Its values here.
Okay,
Is what we got the square root of 3/2?
yeah,
Okay.
right. Square root of 3/2. Just tested out, got the same thing.
Sure.
Just do Schwartz, yes. Here they give an example of a possible real-world use. Your car driving 15 miles per hour, you pass a police car. 4 months later, you pass a second police car, and you're traveling 50 miles per hour. The distance between the two police cars is 5 miles. The second police car nails you for speeding.
Oh, nailed it.
How can he prove you're speeding? Can it be proven?
That's Sue right there.
Well, if he has a walkie-talkie and talks to.
But the speed limit is 50 miles. We'll say the speed limit is 50 miles per hour. It doesn't say that, but let's say it's 50 miles per hour. You go by one cop, the thing you're going within the speed limit. Then 4 minutes later, you pass that second police car traveling. You're still traveling at 50 miles per hour, but you get nailed for speeding. But you weren't speeding when you went past either of those cars. So how can it be proven that you were speeding?
English.
Let's look at this miles per hour, right? That's what you have to do. So 4 minutes later, 4 minutes is how many hours?
It's,
What did he just say?
115.
115.
Point 15?
I thought.
115.
Yeah.
So
115.
0.06.
0.0667, right? 0.067, we'll say. That's how many miles, right? So you want miles per hour. Well, that's how many hours you went. So you went 5 miles per that many hours. So this is going to tell you how many miles per hour you went. 5 divided by 0.067. This is how many miles an hour you were going. How many miles per hour would you go? So the cop, you got nailed for going rounded to 75 miles per hour for that.
So why does it say you passed
19
a
miles
police
per hour.
car and you're traveling?
Because they slow down when they slow down.
So
Oh.
how does the cop justify this in court?
Speedometer.
He says, there's no way you could travel 5 miles in 4 minutes.
If you weren't
And
going.
and what does he cite?
The, what's it called, Rolle's theorem.
Let me think, Rolle's theorem.
Roll's theorem.
The mean
Actually,
value theorem.
yeah, actually something, it would be mean value theorem, and I was thinking what Chloe said, but what it is,
Who's saying no way
Mr. G, next time someone asks next time someone asks you, what are we doing with this in real life, you can give them this example.
yeah, and the strange thing about it is, you've heard it at toll booths, it can be used. Actually, toll booths will use it to buzz people, because they can tell when you pass the toll booth. So it can actually be used for that. Now, the thing about it is, it can be also used in your defense, if you understand, right? Now, according like this, to prove I was going that fast, you'd have to have a starting and ending time to prove by the mean value theorem that I was going that fast, officer. You can't do it, sorry. And so there are different ways of looking at it. And I know it's kind of a contrived example of this, but it's kind of interesting. But people actually have used calculus to defend themselves in court over such
I
things.
believe it, I believe it.
And the thing about it is that I think a jury could probably understand it too.
I'll take it.
Because
I think Rolle's theorem is pretty.
yeah, and that's the thing about this. Some of the things we do in calculus, they're pretty. People understand them, but they're harder to explain. That's what we're trying to do in calculus class. We're explain these things. So now we're given another example here. Let's do example 4.
Okay.
It says, so I want you to go ahead. Now, do you remember what the derivative of sine is? d dx of sine is equal to what?
Cosine.
Equals cosine x. So that's the derivative of sine x. So go ahead and do this one. 0 to pi. You got to find, what do you have to do to test for mean value theorem? You need to know what, the what and the what.
Point the slope.
F of
F of A and F of B.
F of A and F of B and B and A.
What?
And what you need to know, and what do you use F of B, F of A, B and A for? To find the average rate of change. You need to find the average rate of change, and there, use the average rate of change. Set that equal to the derivative, solve for x. You have done that.
Yeah.
And it says confirmed by calculator too. Let me make sure my calculator is in. My calculator is in radians. That's one thing you want to do with when you deal with trigonometric functions. Make sure your calculator's in. Radians.
And then you find the derivative. Oh wait. Two. Oh. And then put
So to me, I get average rate of change of 2, is that right? Yeah. So now we find f prime of x. So we're going to have 2 plus cosine x, right? And if we set that equal to 2, 2 equals 2 plus cosine x. So cosine x equals 0. So x therefore equals
1.
Zero divided by,
so cosine x equals 0. X is going to be, we're between 0 and pi. So where is it going to be? Where between 0 and pi is cosine x equal to 0? Pi over 2. Pi over 2. So find the equation of the tangent line. So that's going to be x equals pi over 2. Our slope is, we have to plug in, we have to go back here. We have to go over here and plug in pi over 2, don't we? So f prime of pi over 2 is equal to 2 plus, what is cosine of pi over 2? 0. So that's 2. So we know that. So that's going to be our slope, right? And then this x value. What is our y value? We got to find our y value. So what's f of pi over 2? So it's going to be 2 times pi over 2 plus what's sine of pi over 2? What's sine of pi over 2? 1. So we have 2 times pi over 2, and this is going to be 1 plus 1. So that's going to be 2 plus pi, isn't it? Or a pi plus 2, we'll say. So now we know our point is going to be pi over 2, comma, pi plus 2. Because that's going to be like 5.14, something like that. And then we take, our slope is going to be 2, right? So what's our equation? It's going to be y minus pi plus 2 equals 2x minus pi over 2, right? So that's going to be our equation of our line, if that works right. So let's go ahead and see if that's right. I get one thing we could do. Let's grab 2x plus sine x plus 1. So 2x plus sine x plus 1. And we're interested between 0 to pi. 0 to pi. And I'm going to go to pi over 2 here. Went to pi over 2, y minimum. We'll go from like -2 to 6. Okay, this graph, see what that looks like. Okay. We didn't go all the way to pi. Let's go to window, get that higher. We'll go to x, y max to 10. Okay, so it should be right, here's pi over 2. So the slope should be 2 right here, shouldn't it? Which should be the average. That looks like it could be it. Let's see if we can go to second, trace, dy dx. And we go right here. Oh, put us right here. This is going to be, that's going to be pi over 2. Our y value is that. and let's go ahead and press enter. There it is. So here's your pi over 2, here's your slope.
That's 5 plus 2.
This is pi plus 2 right here. Everything checks out. So if we go right here, we can go ahead and enter that. If we went and solve this for y, we can go ahead and put it, we'll hit exactly. Well, let's go ahead and do that. So what we do is we add pi plus 2, right? So we go ahead and put in 2 x minus pi over 2 plus pi plus 2.
Yeah.
Right, so 2 x minus pi over 2 minus pi, is it minus pi minus 2? Pi minus 2. See if it's tangent here. Hope it is. No, I don't see it. Oh, it's plus 2. Hang on. Plus. So I got it wrong. It's going to be plus plus. Let's go down and plus it. So that's will be plus here, and this other one, Ben, that's going to be plus
Were
2.
you tricking us, Mr. G?
No, seriously, I have a hard time remembering everything. Does that look perfect?
Yeah, that's exactly.
That'll,
That's perfect. Right?
exactly, that should be on a shirt.
So that's what it looks like. Okay, but to me, what it is, I don't know, is I've been teaching calculus a long time now
No, about what he
and taking
said,
it,
honestly.
and when I was taking calculus the first time, and even now, after so many years teaching calculus, it just seems almost like magic that you're able to do this and figure out how it works.
Magic.
It does. It really, to me, it seems. Then I go to the calculator and I say, okay, well, is the thing going to work? I hope and pray that it does.
Yeah. Sometimes it doesn't work, and then I want to do the calculator across the room.
Well, no, but see, it didn't work in that time because I put the wrong signs for those things, right?
So it wasn't the calculator's fault.
No, it wasn't the cat. It was human error fault.
Human error.
But we figured it out because we didn't see what we expected to see. We were able to fix it pretty fast. So let's go ahead and look at I'm going to leave that up there for intimidation purposes. Okay, why can't you use the mean value theorem for this one? Example 5. Why can't you use the mean value theorem for this? Why can't you use the mean value theorem?
Yeah. Yeah, because it's the same y value for both x. Is that one?
Well, it is, but actually you can use the Rolle's theorem version of it, right? So you can still use Rolle's theorem, but he's right to think that way. But I want to show you something. X to the 2/3 power. Let's go ahead and do that. Clear. So x to the power of 2/3. I'm going to go like this. 2/3. And what I'm going to do is I'm going to go to zoom 6. Okay, why? So now looking at the graph that you didn't know, why can you not use the mean value theorem?
Because there's, what's it called?
What are the conditions of the mean value theorem?
It has to be continuous and differentiable.
It's not.
Has to be continuous and differentiable. Do you see continuity here? Do you see differentiability here? No, you do not. Why do you not see differentiability here?
Because there's a place in which there's those.
Because there's a point. So if you go to a point, a corner, a cusp, or a vertical tangent line, that would disqualify
The whole line.
guaranteeing the mean value theorem.
Across the whole line.
Like it's.
Well, yeah, here, what it is you can't use it disqualifies the guarantee of the use of it.
Well, what if you use a different interval?
Yeah, if we use a different interval, say if we go from 0 to 2,
Oh, that's
well
fine.
then we could do that.
But because -1 and 1, that point is right in between.
Yeah. So it disqualifies at 0, but if you put anything in there besides 0, any other interval that does not include 0, then you could use mean value theorem. So it's example of a disqualifier. So so what you would say it like this: we say f of x is not differentiable for on the interval from -1 to 1. Therefore, MVT does not apply, or does not be guaranteed, does not apply. Okay, and then we come here to the homework assignment for that, which is a nice, good, long homework assignment that has this. So here's what I want you to do. That is a good little homework assignment. All right. Can you do, here, I'll give a small homework assignment.
Here.
Problems 1 and 2.
Okay.
Problems 1 and 2. Could that be a homework assignment for tomorrow?
Okay, tomorrow, yeah.
It should be like a 10 or 15 minute deal.
So we be done with that.
Yeah, I want to get on to tangent lines and stuff like that. So you can go start working on that. That doesn't seem too hard, does it? It's not too hard.
Oh, okay. Thank you for this, yeah.
Rolle's theorem can be applied.
Oh, right.
It says also if Rolle's theorem can be applied, so you can look at that and examine. I'm thinking Rolle's theorem might be pretty good for X. Yeah, I think Rolle's theorem probably works for both of them.
Oh.
Just visualizing what those graphs look like.